Hi everyone. Now let's understand the Thevenin's equivalent circuit and how it can help us to transform a complex circuit into a very simple one for the analysis on how the load will behave. Now let's look at the circuit that we have over here. Okay, we have a 30 volts source with some resistors. Now what we're interested in is the load. So in this case, I have specified the load to be over here, RL, with an 8 ohm resistor. Now, when we say that we specify a load, that means we are interested to find out the voltage and the current that is experienced by the load. All right. So, of course, we can go through the series and parallel analysis, okay, step by step to figure out the current that flows through in this particular branch over here. Okay, and then we will understand the behavior. In some cases, the circuit can be a lot more complex. All right. So what we can do is we can, using Thevenin's approach, we can convert any complex circuit into a very simple circuit. Okay, that means what we want to do is we want to convert this circuit into a very simple circuit that has a voltage source, a resistance, okay, that is then applied to the load. Okay, so the load will still remain the same, which is RL. In our case it is 8 ohm, but we are going to convert the rest of the circuit to an equivalent, which will then be called the Thevenin's voltage and the Thevenin's resistance. Okay, so the key concept is how do I convert the rest of the circuit, that means from the load, okay, or the part of the circuit before the load, to the Thevenin's voltage and Thevenin's resistance. Okay, so let's look at it step by step. So the first thing I'm going to teach you is the Thevenin's resistance. All right, so to find Thevenin's resistance or RTH, okay, the rule is basically simple. You need to remove all the sources you have in your circuit. So for voltage source, okay, so for voltage source, what you must do is you must replace with a short circuit. For current source, you replace it with a open circuit. Okay, so to find the Thevenin resistance, what we are going to do is we're going to follow this rule over here, and we're going to redraw the circuit, okay, with the voltage source replaced with a short circuit. So since we have a 30 volt source over here, we're going to replace that with a short circuit, and the rest of the components will remain as they are, but we will not need to draw the load. So let's proceed here. So here I have a 2 ohm resistor. I have another 2 ohm resistor here and a 3 ohm resistor here. Okay, and where the load was, all right, we will not draw the load, okay, because the load will be removed for the analysis of the Thevenin's voltage and Thevenin's resistance. All right, but for finding the Thevenin resistance, okay, so what we need to do, or the technique, is to imagine that in place of the load there is an imaginary voltage source. Okay, and with this we will analyze how the current is going to flow in the circuit. Okay, so we can see that the current that comes out of this voltage source will flow through this resistor, the 3 ohm resistor. We'll call this I, and at this point what will happen is it will split, okay, into I1 and I2. So it's split into these two resistors over here. Okay, so with that we can say that the circuit, okay, can be redrawn to look like this, where we have a 3 ohm resistor, and the other resistor here is the 2 parallel 2. Okay, and the imaginary source is still here. Okay, so 2 parallel with 2 will give me 1. So the total resistance, okay, or the next part of the circuit will look like this, where you have 3 ohm and 1 ohm, okay, in series with the imaginary source. And since these two are in series, the final resistance over here would be 4 ohm. Okay, so that gives us the Thevenin's resistance, RTH. Alright, so let me again quickly summarize the steps. To find Thevenin's resistance, alright, what we need to do is we need to first replace all the sources. Okay, by following this rule, the voltage source will be replaced with a short circuit, current source will be replaced with a open circuit. Alright, and after that after that what we do is we uh, replace the load. Okay, so the load was over here at the right hand side of the circuit. We replace the load with an imaginary source to understand how current will flow from that point. Okay, so the reason why we do this is we want to understand from the load perspective, what does the load see. Okay, so the Thevenin's resistance is basically the effective resistance seen from the perspective of the load. Alright, so we imagine that there is a source there and we try to analyze how the current will flow. So we can see that the current flows through the 3 ohm resistor plus these two 2 ohm resistors in parallel, and from there we do the series parallel analysis and we can arrive that the Thevenin resistance is 4 ohms. Okay, now that is the Thevenin's resistance. Now let's look at the next analysis, which is the Thevenin's voltage. Okay, so the next one is the VTH, and VTH is basically taken as the open circuit voltage at the load terminal. Okay, so what does that mean? That means we are going to redraw the original circuit, but we're going to keep the load as an open circuit. That means you're going to remove the load and that part of the circuit will be an open circuit. Okay, so let's redraw it and see how it looks like. Okay, so in this case the voltage source is still there. So I have 2 ohms here, I have another 2 ohms here, I have my 3 ohms here, and this is the place where my load was. So I'm going to remove the load and it's an open circuit over here, and I'm trying to analyze what is the voltage that I'm seeing from these two terminals. So that is actually the Thevenin's voltage. Now since this part of the circuit, okay, on the right hand side is open already, there is no current flow, correct? So it's an open circuit, so effectively we can say that there is no current flowing through the 3 ohm resistor at all. Okay, because it is an open circuit at the other end. So because it is an open circuit, the voltage that you see across the over here, these 2 points here, is going to be the same as the voltage you see across here. Okay, because it is already open circuit, no current is flowing through the 3 ohm resistor. Okay, so effectively the open circuit voltage, okay, that we need to calculate is across the 2 ohm resistor only. Okay, because the branch with the 3 ohm is already open circuit. Okay, so this is the voltage that we need to find, the VTH. Okay, so this circuit you can see is a very simple circuit with 2 series resistors. So with that you can calculate VTH to be, so if you use the voltage divider rule, you can say 2 over 4 multiplied by 30 volt, which will be 15 volts. So that is your VTH. Okay, so let me quickly recap. So to find VTH is the open circuit voltage at the load terminal. So you remove the load, alright, and you find the voltage that is seen at the two terminals. So in this case, since I remove the load, the 3 ohm resistor is no longer part of the circuit because it is open, so no current flows through it. And from there, I look at the rest of the circuit and I analyze the voltage that I observe. Okay, so now that you have found VTH and RTH, you can actually now find, or you can actually draw the Thevenin's equivalent circuit. Okay, Thevenin's equivalent circuit. And the Thevenin's equivalent circuit is now a very simplified circuit that just consists of one voltage source, which is VTH, So this is VTH, which is 15 volts connected in series with a resistor RTH, which is 4 ohms. Okay, and then we have the load. Okay, the RL, and the RL is the same as before, which is the 8 ohm resistor. Okay, the RL that we have originally in our circuit. So now you can see that from a very complicated circuit over here, all right, we can now simplify it to a very simple circuit with just a voltage and two resistors in series. Okay, so with that, I can now very easily analyze the voltage across the load and the current through the load. Okay, so the voltage across the load here, VL, is given as 8 over 8 plus 4 times 15, which will be 10 volts. All right, and the current through the load will be 15 over 8 plus 4. So these are simple voltage divider rule and Ohm's law. Correct, which will be 15 over 12, which is 1.25 ampere. Okay, so you can see that right now, okay, by converting my complex circuit to a very simplified Thevenin's equivalent circuit, I can very quickly solve for the voltage and the current experienced by the load. Okay, so that is the key advantage of using the Thevenin's equivalent circuit. Okay, so I hope that this video has given you a better insight into this approach. Thank you for watching. Okay, and I will see you in my next video. Bye.